Welcome to The Explainer. Today, we are tackling a really crucial step in solving differential equations, the inverse Laplace transform. This is it. This is the final move that brings your answer out of abstract math and back into the real world.
So let's set the scene. You've been there, right? You've done all the hard work, you transformed your equation, you solved it, but now your answer is a function of s. What does that even mean? It doesn't tell you anything about what's happening over time. You've basically got an answer, but it's written in a completely different language.
And that's where this comes in. The inverse Laplace transform is our translator. It's the bridge that takes us from that weird abstract S domain back to the familiar territory of the time domain. Our whole mission is to take that function f of s and figure out the one unique function of time, f of t, that it represents.
Now here's the best part. You might be thinking this is going to involve some crazy, complicated integration, right? Well, nope. The secret to the inverse transform isn't more calculus. It's actually all about algebra. It's a game of pattern matching. We're just going to rearrange our f of s function until it looks like something we recognize from a standard transform table.
Okay, so if it's all a game of pattern matching, what's in our toolkit? Well, we've got two main techniques we're going to use to whip these functions into shape: linearity and the real heavy hitter, partial fraction decomposition.
First up is linearity, and trust me, this is your best friend. Just like the forward transform, the inverse is linear. And what that means for us is, if we have a big, ugly function with a bunch of terms added together, we can just break it apart. We find the inverse of each little piece separately, and then we just add them all back up at the end. It's a classic divide and conquer strategy.
But the real powerhouse, the tool you'll be using probably 90% of the time, is partial fractions. This is the magic wand we wave to take a complicated fraction, a polynomial over another polynomial, and smash it into a sum of simple, friendly little fractions that we actually know how to transform. Think of this table as your Rosetta Stone. It's the dictionary that translates from the S domain to the time domain. See that pattern? If your denominator has distinct factors, you get simple exponentials. What about repeated factors? Well, that's where you start seeing a t pop up in your answer. And those quadratics you can't factor, those are your telltale sign that you're about to see some sines and cosines, which means oscillations.
All right, enough theory. Theory's great, but let's get our hands dirty. We're going to walk through 3 examples that cover the most common situations you'll run into. Let's bring this all to life.
Let's start with a classic, a real bread and butter problem. We need to find the inverse Laplace transform of 1 over the quantity s squared minus 9. This is our distinct linear factors case.
Okay, so what's our game plan? Step 1, we've got to factor that denominator. And hey, that's just a difference of squares, right? So we get s minus 3 times s plus 3. Step 2, we set up our partial fractions. Step 3, we do a little algebra to solve for our coefficients, a and b. And finally, step 4, we use linearity to transform each of those simple little pieces all on their own. And boom, there it is, our final answer. See how it works? That a over s minus 3 term gave us a growing exponential, e to the 3t, and the b over s plus 3 term gave us a decaying one, e to the negative 3t. It's a perfect pattern match right from our table. Okay, that was pretty straightforward. But what happens when a factor shows up more than once? Let's look at the inverse transform of 5s over s minus 2 squared. Now, this is a spot where a lot of people trip up, so the setup here is absolutely key. Here's the critical difference. For a repeated root, you need a term for every power. So we have to set it up as a over s minus 2 plus b over s minus 2 squared. Once we solve, we find our coefficients. Now, the a term is a standard exponential, but here's the big takeaway. That squared term, the b term, that's the one that gives us a t multiplying our exponential in the time domain. Remember that. So our final answer has 2 distinct pieces. We've got our standard exponential part, and then we have this second part that's ramped up by t. That is the unmistakable signature of a repeated root in the S domain.
All right, one last example, and this is the big one. What if you look at that denominator and you just can't factor it? It's an irreducible quadratic. This is when we have to pull out our final tool, and it involves some careful algebra, completing the square.
Okay, this is where we do some real algebraic gymnastics. First, we complete the square on the denominator to get it into that nice shifted form. But then, and this is the clever part, we have to massage the numerator so that it also contains that same s plus 3 term. Why? Because that's what lets us split the whole thing into 2 clean fractions. One that looks exactly like a shifted cosine transform and one that looks like a shifted sine.
And look at what we get.
A damped oscillation. This is exactly what you should expect. Let's break it down. That s plus 3 part in the denominator, that gave us the decaying exponential, the e to the negative 3t. And the plus 25, that's our frequency squared, so we get our cosine and sine of 5t. It all fits together beautifully.
So, we've just powered through a ton of algebra. But let's pause and step back for a second. What's the really big idea here? What's the unifying concept that makes all of this so incredibly powerful?
It all comes down to one thing. Just one. The entire secret to how a system is going to behave over time is hidden in the roots of the denominator of its Laplace transform. That's it. That's the whole game. In engineering and physics, we call these roots poles. And these poles are like a crystal ball. Just by finding them, just by seeing where the denominator equals 0, you can predict the future. You don't even have to do the full inverse transform. A pole at s equals 3 tells you the system will grow exponentially. A pole at negative 3, it's going to decay to 0. And complex poles, that means things are going to oscillate. You can tell if a system is stable or if it's going to spiral out of control just by looking at its poles.
So the big takeaway today is that this is so much more than a math problem. This is the language we use to describe electrical circuits, mechanical vibrations, control systems, pretty much everything. The algebra is just the tool we use to get to the insight, and that insight is the real prize. So now, the next time you see a complex system, you know the first question to ask. Where are the poles? Because that's where you'll find the story of what's going to happen next.